Welcome to qnawire.
So here we have a turbine. The turbine bleed steam enters an open feed water heater in a regenerative Rankine cycle at 40 psia. So we're in English units here, and it comes in at 280 degrees Fahrenheit. The feed water comes in at 110 degrees Fahrenheit and 40 psia. And then it all leaves again at 40 psia. So again, we have to have the same pressures everywhere in this so that we don't get stuff wanting to flow back here or something. And then it leaves at 250 degrees Fahrenheit. So what do we know here? What do we want to do? We want to figure out what the ratio of the mass flow um, between 1 and 2, or between 2 and 1. So let's see here. We know that mass conservation says the mass flow rate here plus the mass flow rate here has to equal the mass flow rate out of there. And then we're going to assume that there's no heat transfer or work on this thing. And so we have the energy flow in must be the energy flow out, which says that m1 dot times h1 plus m2 dot times h2 has to be m3 dot times h3. Now we know M3 is M1 plus M2. We can plug that into there. And so that eliminates M3. And then we get a ratio. We can then get a ratio of M2 over M1, or M dot 2 over M dot 1. And that winds up being H1 minus H3, all divided by H3 minus H2. And we can, again, we have two thermodynamic properties at every position here, so we can look these up, and these are just in BTU per pound mass. And then so plugging everything in, we wind up with 0.1747. So that means that we need, let's see, about 15%. Well, we want about 15%. This needs to be about 15% of this. So we need to, basically just have about 15% of this would essentially be the in the end out here would be what was going kind of go through the turbine or go into the turbine. So and this would be what we would let's see here, bleed off of the turbine. So again, it actually might be a better analysis to look at M2 over M dot 2 over M dot 3. But here, in this case, basically, we know that we have to have the ratio of the cold water coming in. We need about 15% hot steam coming in, and then the colder water. And notice it's interesting too because if you that this is essentially why things kind of work is that look at these temperatures, right? You only need by mass 15% of this steam by mass compared to this liquid water here to get the temperature up, to raise the temperature a lot. And so it's just because steam has so much more energy in it, basically because of the enthalpy of vaporization for water is very high. So you get basically it winds up, I'm assuming this is superheated vapor. I didn't look it up, but it basically winds up being, might be two-phase, but it definitely winds up being very, you basically wind up boiling a lot of this water by mixing it with all this steam. Now, that being said, this is a mass flow rate. So, we know the volume, the specific volume coming in at 2 is going to be like 1,000 times that coming in at 1. So, your volumetric flow rate is a much different story. But a mass flow rate, we have about 15%.